Okay, now it should be working. I don't know what my microphone default settings got changed. Anyway, hi everyone. Um I hope everyone is having a nice Friday. Today, welcome to the third installment of my Haruhi series. Today we're going to be talking about particle physics. And towards the end, I thought I wanted to do a giveaway. I was a little bit unsure if we should. Thanks for following T-Mord. I hope that's how you say it. T-Mord. And I was thinking of leaving it up to luck. But I said, I think I will do a giveaway, but only for people that stay through the whole stream and pay attention to what I'm saying. So, the giveaway is going to be in the format of there's going to be a Kahoot quiz, and the person that wins. Thanks for subscribing, Evangelion. Glad to see you again. You're not partying anymore. But yeah, so hi everyone. Hi Daliard, Z10 Eos, Zioas. I'm so bad with usernames. I'm so bad. Like every single time I get just everyone's username wrong. Hi Plan from Space. So hi everyone. So I'm giving away this really cool CERN lanyard. So it's officially licensed. It's not like, I mean, it probably was made in China, but I didn't get it off of like a bulk AliExpress thing. So pretty cool. If you guys are interested in particle physics, I think this would be a pretty cool thing to have. But yeah, so I'm going to be giving this away to whoever wins the Kahoot quiz towards the end. So I will explain a little bit more how that's going to work later on. I just left a little pinned comment so that people that enter know that there's some sort of giveaway going on. At first I was like, should I do it as like a follower goal or something? But I was like, I don't know. I kind of just want to give it away on the particle physics episode just for fun. Also, if you hear something going off in the back, it's because I have like a new like scent sprayer thing. So I'm sorry if the mic is picking that up. But anyway, hi Fuxbao, hi everyone. I'm just gonna pull up the presentation. I'm gonna first just go through the main things I always go through. So, thanks for so much. But yeah, so I'm just gonna go through the things that I just go through every time. So I'm calling this series Laid Back Physics, Bouken, Desho, where we're looking at the first opening for Haruhi Suzumiya, and called Bouken Desho. And I don't know. Okay, wait, why is it failing? Every single time it's been fine, and now it's being weird. Okay, now it's fine again. So the Haruhi opening. The Haruhi opening has a bunch of funny equations and stuff in the background, and what we've been doing for the last, I guess now a month, I guess I started it 3 weeks ago actually, is finding all of these equations and little symbols and so on in the back and trying to explain a bunch of them, especially the ones that relate to particularly my field of study, which is physics. Hi Dunder, Bitchel. I always get yours wrong. I'm so sorry. I am not Dutch. I'm so sorry. Okay, no worries, Fuxbao. It's okay if you can't stay the whole time, but I hope you enjoy, and good luck at work. And hi Darren. So what we've been doing is having a look at all the equations in the back and trying to relate them a little bit to Haruhi. So the idea of this series is to, first of all, document the why is it being weird again? Document the background equations of Bouken Desho, because I haven't seen anyone do this so far, and hopefully deliver a little bit of an explanation about the meaning of these equations. And lastly, I if possible, I want to tie them together with maybe themes of the series, maybe shed some light as to why the creators of the show decided to put them there. So, okay, why is this being so weird again? Anyway, so today we're going to be looking at particle physics. This is really complicated and it looks really complicated, but this is not really what we're going to be talking about, not this equation itself, but this is the standard model of particle physics Hamiltonian, which we will not be discussing in depth. I have very superficial knowledge of it, but I just thought I would put it there. If you go to any like particle physics building, they will probably have this framed somewhere. Just wanted to show it to you guys. All the equations that we'll be looking at are a lot more understandable. So yeah, not Arabic. This is, maybe you guys recognize a couple of the symbols. These guys are simply wave equations. We discussed a little bit about those last time. This is a potential, but we are not going to be talking about this particular equation. Just thought I'd include it because it's very, very particle physics. You know, particle physicists are very proud of it, I will say. So our first equation, our first real equation, is going to be the classic wave equation. And funnily enough, this equation was included, as far as I could count, 3 different times. Just the same equation, but formulated slightly differently. Just differences wise, just the notation a little bit, and also they included a general s velocity. Here they included the velocity of light, but the speed of light, but in essence, it's the same equation, so we're only going to be looking at it as thank you for subscribing, Moogie Pilled. So let's get started. So let's just discuss, what are waves? Why do we need an equation for them? Like, what are we talking about? So actually, one person mentioned last time, like, oh, this, like, you know, this wave function that we have in quantum physics, is this related to water waves? And it's not quite related to water waves in that sense, but it is related to this type of waves, which is just a regular wave equation that you use to describe any wave, such as these water waves, for example, which are just radially symmetric. Like for this one, for example, when you put a little drop of water, it spreads in like little circular waves. Or then we have, like, for example, sound waves. Or we talked a little bit more in depth about electromagnetic waves. So a little bit more intuition. So we talked about waves a lot last week, but just, you know, what do we even mean when we say wave? So by a wave, we mean a wave that is traveling both in space and time. It could look something, the function for it could look something like this little function right here, just, you know, just a nice little curve. The important thing is that this function depends on both position, which here we're calling q, just to keep the notation that they used in the show, and t, which is the time. So here we have our coordinates q and our wave equation, and here we have the wave equation, but it's also, not only is it changing in space, not only is it moving in the space, but it's also moving in time. So we can imagine it as something like this, which is traveling both in space, but also in time. So that is the key thing that we need to understand about it, which leads to basically 2 questions that you can ask to this equation that describes your wave, which the first one is, you know, I have a wave, and I am interested mainly in, oh, thanks for subscribing, Plan 10 from space. So we have 2 questions that we basically can ask our equation that describes our wave, and that is, first of all, what is the position of my wave at a particular time point that I am interested in? And then there's a second question, which is, when is this wave at that particular point that I am interested in? So for one, I'm more interested in a particular time, and for the other one, I'm interested more in a particular point. But just from these 2 questions, we can gather some intuition that these 2, position and time, have to be related in some way, because you don't just ask, when is the wave? No, when is the wave what? When is the wave here? Okay, that makes sense. When is my wave passing through this specific point? Or in the same way, you can't just ask, okay, where is my wave? Okay, where's my wave? When? At what point? I for example, yell, and my sound waves travel through both time and space. My question doesn't make sense if I don't describe both things at the same time. Thanks for subscribing, Sinister Fuath. Thanks for being here. So, now that we have these two questions, we can ask a more general question, which would be, what really determines how my wave is moving? This relationship between position and time, how do I relate these two things? And that is where our awesome wave equation comes into play. So this, I won't get into the math, but it's a partial second order differential equation, for anyone that sentence makes sense to. But by partial, it just quickly going over the notation, by partial it means that this derivative is a partial derivative because my function depends both on q and on t. So I'm only deriving part of my dependence. Similarly here, I'm only deriving the part that depends on q. And second order because we have a second derivative. Just to briefly explain the notation, that anyone that maybe looked at partial differential equations or just differential equations but maybe didn't hear this language. But anyway, so the main thing about my wave equation is that it tells me how my change in time, how this, traveling through time, the evolution of my wave through time is related to the change of the wave in space as well. So that is already a very powerful tool because we're already pretty much relating one change to the other change with just one factor in between, which is simply a velocity factor. So, we can take the change in time as the evolution of my wave through time, and we can talk about the change in space as sort of a curvature, which is then in that moment, like the actual local property of the wave, of how it's basically changing in space, how it curves in space. And this directly tells me how it changes in time with just this tiny factor, which is the velocity of my wave. So here we simply have a c because we're mainly talking about electromagnetic waves in the presentation. So I thought it would be just better to keep that notation and relate it directly to, directly related to electromagnetic waves. But this velocity is not, this velocity is dependent on what medium my wave is propagating. Also, it also, like, through a medium, certain wavelengths of the wave actually propagate differently. So this velocity is sometimes not as rigid as just a number, but if we're looking at electromagnetic waves in vacuum, then we have the speed of light, which, as we've talked about a little bit before, we denote with a small c. So let me know if there are any questions thus far. From this point onwards, now that we've kind of described what this wave equation means, more or less, I just want to briefly go over a little bit about and do like a little bit of a recap of what we discussed last week on electromagnetic waves. So we have a whole spectrum of electromagnetic waves, which is used because we characterize waves by their wavelength or by their frequency. So the spectrum basically goes from the lower energetic range, which includes like radio waves or microwaves, which have a longer wavelength, and also they have a much slower frequency. So these periods are much more separated. And following this, we also have, for example, thank you for following Aphelion. Sorry, I have my chat pulled up here and I just got a little bit confused. But anyway, so following this, we also have the infrared, which, as we also talked a little bit more in depth last time, 2 weeks ago, which basically is more so heat radiation, like from fire, from the sun, etc. And then we get into the visible light spectrum, which are the wavelengths that we can actually see with our own eyes. Because some of these we detect in different ways. Infrared we can detect by just sort of feeling. We feel warmth, we feel the warmth of radiation, but visible light, we can actually see it and capture it with our eyes that are basically integrated detectors. Hi, Riyadh. Hope you're having a nice Friday. Following, when we get to higher frequencies, meaning shorter wavelengths, we see ultraviolet, X-rays, gamma rays. All of these sound kind of scary, and this is because they have higher energy, so they can be damaging to our cells. For example, like they always tell you, wear sunscreen, you don't want to get skin cancer and so on. So this is precisely why, because they're higher frequency, meaning more energy. But yeah, so following this, just as a little reminder, we characterize waves by their frequency, aka their wavelength. So high frequency means short wavelength, low frequency means longer wavelengths. And just for the sake of completeness, we relate frequency and wavelength for electromagnetic waves through just an inverse proportional with the speed of light as a factor. This is just, for the sake of completeness, sake of describing waves really nicely, hopefully. But this brings me to our first particle that we have been kind of talking a little bit over about, but haven't really truly said, okay, this is a particle in the model of particles, which is the photon. So last week we discussed how discussing electromagnetic waves led to the creation or the invention of basically quantum mechanics and quantum theory. And this means, so this basically means that from what we described last week, waves carry their energy in packets of quantized amounts of energy. And this is what we call a photon. So our first particle that we've discussed is a photon. Jusser asks, what about frequencies in between? I imagine categories change smoothly. Yeah, in general, yes. There are some broad categories that are typically followed, but as we know, you could always have .00001 and then, okay, which one is this? It is not too particularly important, so to say, for the majority of experiments, applications. You typically will use frequencies that are really well defined in your experiment. Like, for example, when you want to excite a particular transition in an atom, you typically know the range of frequencies that can be applied to this particular use. And, if it is not, the in-betweens are not too important. It's just a brief, like just some general categories. But basically where they change, at least for our application, what we're discussing, or at least for the majority of my physics life, has not really been too relevant. I don't know if there are any issues in labeling them different names and so on. But yeah, I don't believe that is too controversial, so to say. But yeah, so our first particle that we have been discussing is the photon. And here on the right, you have this nice little rounded description of all the elementary particles, and this is what is called the standard model of particle physics, and this is basically the heart of what we will be discussing for the rest of the stream. But for right now, we've only really covered this little guy, the photon, but today I hope we can bring a few more pieces together. So let me know if there are any questions until then. Please ask questions, especially if you want to join in the quiz at the end. I think it would be useful to ask some questions. But I think this was probably the most, we just covered maybe the most, the part that you guys will find maybe the least interesting. Okay, just an equation that tells me how waves move. Okay, yeah, to get into like the more interesting stuff, we really have to just discuss the math and I feel like that's kind of out of the scope. So I just want to introduce you guys to our little guy, the photon, that mediates electromagnetic energy as we have been describing thus far. So let me know if there are any questions. Meanwhile, trying to take notes as best as I can, of course. Meanwhile, I just want to mention, first of all, in the center of all this, we have this giant H. This, maybe you guys have heard about it from maybe just pop culture, etc. This was a big thing when it was first experimentally discovered. If you guys were alive in 2011, I think 2010, 2011. This is the Higgs boson, and I just thought it's funny. You know, another H. We've been talking about a bunch of H's, but same follow-up is, oh my gosh, I am covering this entire note. I am stupid. I will just read it out loud anyway. So a lot more of the standard model is also covered in the second hierarchy opening. So let me know if you guys would be interested in me continuing this series beyond what we have covered so far. I plan on at least doing one more part, which will cover the rest of the equations for the first hierarchy opening. But if you guys are interested, I will for sure cover the second hierarchy opening in the near future. So just give me some feedback, send me a message, DM me, reply, anything like, yeah, I would love for you to continue, and I will try my best to continue. Also, because I'm covering the screen, if you guys are interested in downloading the slides, I have a Ko-fi page, which is also linked in my Twitch, and I have the slides for each one of the parts that I have covered, and maybe they help you take notes, also access some of the links that I provide, which today I will provide a few links with some interesting content. So, and also if you guys just want to support the series because you think that it's cool or whatever, I would very much appreciate that. But yeah, so this is it for the, I guess, introduction. Let me know if you guys have any questions. I will also answer in between just talking. But main takeaway from the first part, we have a little guy called the photon. He is part of the standard model of particle physics, and he mediates electromagnetism. I think that's kind of the main takeaway from from the first part. When is lunch? Right now for me it's 10:30 p.m. So it was long ago. You missed out. But yeah, so following this, we have a really famous equation, so famous that it's in my water bottle. I think you guys might be able to see it. I hope I am. Yes. Okay, wait, I slide my finger down, and now, yes, now you guys can see it. E equals mc squared, the energy mass equivalence principle. So, let's talk about it. Oh, why is it glitching? Okay. So Einstein's energy mass equivalence plus AI, yeah, E equals mc squared plus AI. Don't forget about that. So you guys have probably seen this equation somewhere, like on LinkedIn. Okay. I'm sorry. Okay, I'm seeing the stuff on my iPad just to make sure I can read the chat because I don't have a second screen and sometimes it just dies. Anyway, so Einstein's energy mass equivalence principle is one of the most famous equations in popular culture. We in fact have seen it in some other anime, like Dr. Stone. So this is the equation that he wears on his little outfit. Jacket, outfit, I don't know. The Sanku wears on his little thingy. And the foundations of this equation basically come from things that we have briefly discussed before. First of all, we never went too in depth into Newton's laws of motion, but just, the idea that if I, for example, go up a hill, I have a certain potential energy, and when I go down a hill, when I'm going down a hill, I have a certain kinetic energy from my movement. And also, the second factor is something that we've discussed really in depth and just briefly mentioned with the photon situation and everything that we discussed last time. The fact that you can have energy and electromagnetic waves, which are not matter. They are non-material. They are simply a electromagnetic wave, or like this electromagnetic wave that also has these particle properties, this like quanta of energy, and it doesn't have a mass. But how does it have energy, but it doesn't have a mass? This is kind of confusing, and this is something that Einstein thought about in 1905. He proposed this idea that basically mass and energies are two sides of the same coin. Frolic says, I see it all the time in my dad's favorite anime, The Big Bang Theory. That is certainly a good anime. Just as good, okay, never mind. Anyway, I was just gonna say that, the Steins Gate dub is kind of Big Bang Theory coded, if you guys have seen that. The dub specifically, the dub. Just watch. Anyway, that is a little bit off track. We can discuss this afterwards. But yeah, so energy, mass, two sides of the same coin, E equals mc squared. Okay, what does that mean? What are the implications? I thought we should illustrate it with a very straightforward example. I have a AA battery, and I'm charging it. So the energy gained by my battery increases the total mass of the battery, but it is too small for us to notice. So what does this really mean? I did a little bit of a computation. I have a AA battery, which according to Wikipedia has around 3 watt hours of energy. I take my watt hours of energy, I convert them into joules. So that would be 10,800 joules of energy. And I take my energy mass equivalents to calculate this what you'd call basically relativistic mass gain in this case. So my mass is equal to my energy that I am putting into my battery divided by c squared. So the speed of light squared. And this is about 1.2 times 10 to the minus 10 grams. So definitely nothing we would ever notice. But then I thought, what if we have a really, really large battery? So I looked up what is the biggest electrical battery that you can find. And for my knowledge, it's, at least that is readily accessible to the public. It would be, for example, the battery for an electric SUV. And that would be about 200 kilowatt hours of energy according to this electrical vehicle guide website. You guys can access this, I hope, in the slides. And anyway, so if we fully charge our battery, we assume just, perfect, it's using up all of the battery, it's charging up the entire battery, it would still be a mass change of only about 8 times 10 to the minus 6 grams, so a few micrograms. And depending on how precise your scale is, I don't know if you could actually measure this as just a lay person anywhere. Your scales will usually not really be this accurate. But so this exists for our day-to-day applications. Not really something that matters too much, honestly. If you guys want to look at it a little bit more in depth, I did include this Stanford EDU document, an article that goes in depth into the history of this mass energy equivalence principle, and it also it talks about it way more in depth than I will today, but it's not too math heavy for anyone that is interested but maybe doesn't have a math background. Definitely recommend that one. But anyway, when does this actually matter at all? Like, if I have a battery, it doesn't matter. If I have a super huge battery, it also doesn't matter. But when does it matter? It matters when I have really, really tiny masses. So where this relativistic mass change becomes a lot. Masses are at really high energies. And just as a little exercise, could anyone tell me an example of somewhere where we have really, really tiny masses? Think like atomic scale masses or smaller. And really, really, really high energies. So maybe if you guys could think of an example. I thought about 2 examples. One of them I didn't include because maybe it's a little bit violent. So I just included one example. But if you guys can think of some examples where this is the case. Black holes. I'm not so sure. Black holes. That's a good question. Definitely some relativistic effects going on in there, but I guess more of a gravitational situation, right? I guess not in particular where we're talking. The photons have no mass, in fact. Photons have no mass, but you're kind of going in the right direction. It has something to do with particles. So one of the examples I thought of was atomic bombs, where, you have these reactions that cause fissions and, you have a bunch of energy coming out. And then I thought, I don't know if I want to really emphasize that too much. Maybe I'll just briefly mention it. Neutrons, another good guess. Also kind of related to that. But it is actually at particle colliders where you have really, really, really tiny masses. So this is, for example, I believe this is the Atlas. And they, at CERN, they have one of the biggest particle colliders, and they collide really, really tiny particles such as, especially for the most part, protons. So they accelerate protons to really, really high energies. They boom, clash them, and they look at the reactions. And this is precisely what we're going to be talking about right now, more in depth, about what they're actually looking at over there. So, do you guys have any questions thus far about the energy mass equivalence principle, about particle colliders, and so on? Let's see what else you guys said. Lasers. So lasers are actually basically photons. So what you're getting is really like a really precise frequency of photons, and that's why they typically have very defined colors. They operate in a very narrow wavelength, and that's what makes them really useful for a lot of applications. But yeah, let me know if you guys have any questions thus far. Yeah, I'm a foreign Malayser, yes. old head reference. I guess kind of fitting for a Harhi stream. But yeah, so let me know if you guys have any questions thus far. I guess main takeaway here is we can relate energy, like as in movement energy, to masses, and also just, when something gains energy, it also gains mass. And that's kind of the main thing that we like. Basically, these two things are two sides of the same characteristic, so to say. But yeah, so, okay. What are the potential future applications of particle accelerator tech? So there are applications, particularly in the medical field. that is definitely not my expertise, but I do know that they have attempted and have been actually relatively successful to my knowledge with with applications of particle accelerators in destroying cancer cells and so on. So there's that application. I'm not very much of an application person, but I was actually talking about this a little bit on Twitter, that whenever someone asks me what the applications for what I'm working at it and working in are, and I'm like, I don't know. I don't know if there are any. Like, it's just cool. It's just cool, you know. But yeah, I know there's some research being done on the medical side. I just don't really know the specifics. I know some cancer treatments with like positrons and also stuff like that. So if you guys are interested in the applications, I think that might be a good place to get started. Does dark energy have mass? So this is more of a cosmology question, this whole dark energy situation. This is not really something you deal with a lot in particle colliders, but just kind of going over a little bit more so on the dark matter side of things, not so much dark energy, because dark energy is basically, it's not the same as dark matter. Dark matter is basically what they believe is some sort of probably a particle which we cannot see through anything except for gravitational forces. And they are actually trying to find some sort of dark matter particle sometimes at colliders. Whether that will, whether that is very close to happening, to my knowledge, not really. Dark energy, I actually know not a lot about. This is more of a cosmology problem, and again, is basically a part of energy from the energy that you see in the universe that you can't really explain. I don't think this has been attributed more so to a particle, but I don't know what the research direction is going in for dark energy. So sorry if that doesn't particularly answer the question. I'm just not much of a cosmology person, I guess. Are we talking about Large Hadron Collider technology? I'm not going to talk about how colliders actually work for the sake of this presentation, but I will discuss a little bit about how they find particles in colliders. So you'll get a little bit of that, but I'm not going to be talking too much about the physics of how colliders actually how the whole, it's a complicated thing. They have these, really, really giant magnets that help direct particles and, accelerate them. It's pretty crazy. So this is not really going to be discussed here, but I will discuss a little bit about particle detection. There is something I always wondered about particle colliders. Do they explode or something if things go wrong? So not explode, but they definitely, they are complex machines and things can go wrong all the time. More so in the sense of, things degrade, parts have to be changed, and things along those lines. Explode, not really. I mean, when they built the LHC, the Large Hadron Collider, there was some discussion of creating a teeny black hole that would swallow all of Switzerland. But that physicists never believed that would happen. It was a little bit more of a fear mongering. Yeah. They go through a lot of safety checks and so on at these places. Is there different parts of particle accelerators, right? Yes. So there are, for example, linear accelerators, which just accelerate particles linearly, or for example, the LHC is actually a circular accelerator. So yeah, there are some different accelerator geometries that can be used. I remember the movie where they made antimatter using the Large Hadron Collider. Maybe you're talking about Angels and Demons. I think that was the name of that movie. I personally didn't watch it, but yeah. we will be discussing antimatter. It is in fact where we are kind of leading to right now. And yes, antimatter is regularly produced at CERN. So yeah, I haven't watched that movie, but as I feel like anyone any physicist has seen that scene where they actually, like, I think they produce antimatter and trap it or something, and like they show like just like a big like blob of stuff. I don't know, something along those lines. But we're actually getting into antimatter right now, so that's a good segue for the next topic, which is positronium, which is this little guy right here that is composed out of an electron and some strange creature called the positron. So let's discuss a little bit what the heck that is all about. So let's talk about matter. Before talking about antimatter, we have not even really discussed a good segue to our sponsor. Matter makes everything possible. The standard model is a theory, basically our model of physics that describes all matter and forces in the universe, all the forces that affect matter in the universe. And this is our model. On the right, we'll go through it step by step. So we have two main groups of elementary particles. They can be categorized into bosons, which include, for example, the gauge bosons, and these are force carriers. We saw, for example, our photon, which carries electromagnetism. Similarly, we have the gluon, the Z boson, the W boson, and these all carry some sort of force that affects matter. For today, we already discussed the photon a bit. We're going to be discussing the gluon a little bit superficially, but bosons are not going to be our main concern for today, but I just should mention it. And secondly, we also have a second type of boson here in our elementary particles. By elementary, I mean they cannot be split into smaller particles. That's what elementary means. And our second group is the Higgs boson, which has a group of its own. It's just the Higgs, which is the originator of mass. Tell me if you guys are interested in the difference between gauge and mathy, but maybe I can just superficially go over it. So yeah, Fermi had so much stuff named after him. Yes. This is just to go over it, this is named after a whole part of statistics, of basically particle statistics, called Fermi statistics. And the reason why these are called fermions is because they follow Fermi statistics. The reason why these are called bosons is because they follow these, I think called like Bose-Einstein statistics, whatever, just little mathy statistical thing. And this all is related to the spin of these particles. Yes, the Fermi-Dirac statistics. Very right, Frolic. Maybe you saw the 1 over e to the power of blah, 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 and then one has a plus, the other one has a minus. I'm sure you probably saw it somewhere, especially when, I believe maybe if you saw stuff on entropy, maybe you discussed that a little bit. Anyway, going a little bit beyond the scope, we're mainly going to be focusing on our fermions, which are our matter particles. So matter particles, we can divide them into two elementary groups. First of all, we have quarks, which are the up, the down. The up quark, the down quark, the charm quark, the strange quark, and the top and the bottom quark. Awesome names. They have really cool names. We have to give them that. They got very creative with naming all of these. For for everyday matter that we see, we are only dealing really with up and down quarks. They make up our protons, they make up neutrons, and they also make up other particles. I personally am a big fan of the charm quark. Really nice name. But charm quarks and strange quarks are have higher energies than the up and the down, and are only really seen at particle colliders. Or at some other sort of high energy experiments, such as looking at cosmic rays. So on. And similarly, the top and the bottom quark have even higher energies, making them even higher to actually be seen, which is why for our everyday life, we only see up and down quarks, really. Yeah. So those are all our quarks that make up things, and they're only ever found stuck to each other. We will discuss in a little bit why that happens, but we're just giving you a little bit of an overview right now. And now let's just go over into our last group, which are the leptons. So the leptons, again, we have 3 families of leptons, and I think there's one that I hope you guys are familiar with, and that is the electron. So the electron is a lepton, and it has a little friend, which is called a electron neutrino. So this guy is a neutrino. Maybe you guys have heard about neutrinos. They're really, really tiny particles, hard to detect because they only interact through the weak force. But there's neutrinos pretty much everywhere, all the time, etc. But yeah, so we have 3 families: the electron with its respective electron neutrino, the muon with its respective muon neutrino, and the tau with its respective tau neutrino. So yeah, let me know if you guys have any questions here. It's a big overview. Just wanted to cover sort of everything at least a little bit. So maybe some questions will pop up. What is my favorite fermion? That's a hard question. Honestly, I like the muon because it is really cool It's a really cool particle experimentally. And also because I like the name, because it's like kind of like mu, like sounds nice. And I also like the charm and the strange quarks because they have really cool names. You just have to give it to them. And what type of collider can you achieve collision course of love? Actually, we named the song kind of after what I was working at a little bit. So, yeah, so kind of funny. Also kind of after Fall Out Boy song. But yeah, so let me know if you guys have any questions up to now. If not, we will proceed from diving a little bit more in depth into these ideas of matter and so on. So if we don't have questions in matter, we can talk about antimatter. So every matter particle, every fermion that we discussed, has an antimatter counterpart. And this actually theoretically came from putting together elementary quantum mechanics and relativity. So they came up with an equation named after Dirac, the Dirac equation. He came up with a way to describe quantum mechanics, and from this equation, you can derive that there are 2 possible energies that can be found for any fermion. And these 2 energies, one is positive and one is negative. And this had a few different explanations that people tried to give, but the main and the one that people sought after is the fact that there could be an equivalent particle which, instead of having, for example, for the electron, instead of having a negative charge, it had a positive charge. And this is particularly this guy here called the positron, which will be our main focus of this part of the presentation. But every single fermion has this elementary anti-fermion. So we have anti-up, anti-down, anti-charm, anti-strange, anti-top, anti-bottom, positron, electro, anti-neutrino, anti-muon, muon, anti-neutrino, anti-tau, and tau. So some questions. Do you know why they got the names Charm and Strange? I probably heard it at some point, but I honestly do not remember it. Maybe we can look it up towards the end. But I personally don't remember it right now. But I feel like I probably have heard it at some point. But yeah. I do have a lot of anti-charm inside of me, I believe. That would explain some things. Maybe Daliard is a freak of nature made up of anti-charm particles. Maybe we need to experiment on him. But yeah, let me see. Let me just have a quick search as to maybe why the charm and the strange were called out. Let's see. So they named the strange quark because they found these particles that exhibited really long lifetimes compared to other particles of similar mass, and they basically just thought they were strange and called them strange particles. And that's kind of that name came about. And the charm quark came because the theorists that described the charm quark first were charmed by how beautifully it explains certain anomalies in particle physics. So the names expectedly came out of what you would expect. and after that, they just kind of gave up. They just said, okay, top and bottom, I don't care. I don't care. I don't care anymore. So I think the second generation of particles definitely had a little bit of a, they were definitely their favorites. Let's just say they were charmed by how nice it was. But yeah, I hope this made you remember the names. Anyway, our main focus is going to be this little guy called the positron. That is the same as the electron in a lot of ways. Like, it has the same mass, same description of decay, other things that I don't really want to get into right now, but it has a main key difference, which is it has a opposite charge. So it's basically a positive electron, and that's how it was actually first experimentally described. Now, honestly, now I'm scared to ask the difference of the up and top quarks. So maybe I didn't make it too apparent. You guys can actually see it here a little bit more clearly, so I should have emphasized this a little bit more. This is the mass given in MeV over c squared, because of this mass equivalence principle that we looked at. But yeah, so bigger number means bigger mass. So we go from 2.2 MeV for the anti-up, or the up, it has the same mass, into 1.28 GeV, so a lot more. And then we go into 173.1 GeV, so a lot more mass. And the rest of the quantities are the same because they are the same for each of the up, charm, and top. They have, in the case of the anti-up, it has -2/3 charge. Then, yeah, right, this is the charge, I believe. Yes, this is the charge. For the anti-charm, same charge and so on. And then for the anti-down, it's 1/3. For the down is -1/3. But yeah, anyway, so the difference between all of these is really mainly the mass. So each family we get higher masses. So that is the main difference between the up and the top, or the anti-up and the anti-top. And to summarize, this is basically why we see our matter is made up of up and down quarks. So our protons are made up of up and down quarks. Our neutrons are made up of up and down quarks. And this is because they are energetically favorable because they are lower energy. Same thing the lepton side of things. So this is our beautiful model. As we can see, the up and have the same mass. The charm and the anti-charm have the same mass, and so on. And the only difference here is their charge. So their charge, the up quark has a 2/3 charge, and the anti-up has a minus 2/3 charge. And now our electron has a -1 charge, and this means -1 basically elementary charge. We can get into the specifics, but just it has a negative charge, and the positron has a positive charge. So these are our two main culprits of this part of the presentation. So let's first talk about this positron guy. So he is like the electron, but positive. So the guy that discovered him, or discovered it, sorry, I'm gendering a positron. The guy that discovered the positron, Carl D. Anderson, in 1933, he very nicely wrote a paper called The Positive Electron, which is a great name for an electron, which is, instead of being negative, it is positive. So this was the first experimental confirmation for our little guy, the positron, and this was an experiment conducted inside a cloud chamber. So cloud chamber, they were really popular back then. They were really popular in like the 30s, 40s. We'll see another example of that in a second. Cloud chamber experiments, basically you have this chamber which has inside a super saturated alcohol vapor, which is really, really cold. By alcohol, I mean like, something like ethanol, something along those lines. And when you have a charged particle with a really high energy go through your chamber full of this super saturated alcohol vapor, you will see that it ionizes these basically alcohol vapor. And what happens is that when it ionizes it, it condenses, leaving a trail that you can actually capture with a picture, which is exactly what you see in this image. So this was the first ever image of a positron captured by Carl D. Anderson in 1933. And here I linked the original paper by him. So yeah, this is the first image that they ever captured of a positron, and this was a huge discovery. It was very revolutionary at the time because it was the first experimental confirmation of antimatter, in fact, and this earned Carl D. Anderson a Nobel Prize, actually. So really, really cool, really cool stuff. So do you guys have any questions about this? I kind of briefly went over this cloud chamber situation, but let me know if there are any questions. But basically, this is our first experimental confirmation of, yes, we see this, we see these strange particles that are like the electron, but yeah. Hi, just Kyle. Thank you for following. It would not be a cool way to get drunk, I don't think. I have luckily never been drunk myself. But it's probably not advisable to, I think you would probably, I don't know if you would die, but I don't think you should be drinking some really, really cold, supersaturated alcohol vapor. Do not sniff the super cold, supersaturated alcohol vapor. But yeah, so we know electrons. We've discussed them. We know them from our everyday lives to some extent, electricity and so on. And now we know positrons, also experimentally viable, can be seen. And now, what happens if you put them together? So when you put matter with its antimatter counterpart together, you get something called annihilation because of conservation. So this is what the reaction looks like. We have our electron and our positron, and what we get out is normally in this sort of in just a regular low energy case, what you get is an annihilation into two photons, which each carry about 511 keV of energy each. And this is a strange reaction. I have a matter particle and I just get energy after it. I just get some electromagnetic energy. That is kind of weird. And this ties into what we discussed previously, which is this energy mass equivalency principle. So we have our mass, we have our masses of the electrons, which in this case, we're kind of saying that they are kind of at rest or not moving very fast. And they basically collide with each other and annihilate, and they produce just photons, which is pretty crazy. And also some just as a little side note, some other processes can happen if energies are high enough, for example, in colliders. So you get, instead of two photons, you can get some other funny stuff because of this energy mass equivalence principle. But yeah, so any questions about this? I didn't know if I wanted to include much about this, but I thought maybe someone would ask. But basically the question of, if matter and antimatter annihilate, like it's kind of weird, like why do we see matter? Why is there no antimatter? Like, did they all just annihilate? Like, what the heck is going on? And this is actually an open question in physics. And yeah, would be nice to know. I could talk a little bit about it more in depth, but would be nice to know what happened to all this antimatter stuff. But moving on, now we finally get into the little picture of the Harhe opening. This is something called positronium. So this is a temporary bound state between an electron with our positron. But because there is no force preventing the annihilation, this is only stable for a short amount of time. So, the positive charge sees this negative charge. If the conditions are suitable, it can cause this sort of bound state, which only lasts for somewhere between a few picoseconds to a few nanoseconds, depending on basically the type of positrons, which depends on the type of positronium, which basically depends on the alignment of the spins of the electron and the positron. Sorry, I'm losing my voice. I've been talking too much. But anyway, so this positronium that you see in the Harhe opening is also what is known as an exotic atom, which is basically where you have an atom is a nucleus, which is composed of, for example, just a proton, and then it has an electron spinning around it. But an exotic atom is when you have something else. So, for example, here we have this electron with our positron kind of spinning around each other, and this is very exotic and very weird, like Harhe's interested in. So I think they particularly chose positronium because it's atoms, and it's just kind of weird and quirky, and it really goes against a lot of things that you initially think about, like it's just a really strange, it's a really strange object, you could say. So this has been our little bit on matter, a little bit of antimatter, and let me know if you guys have any questions. following this, we will talk a little bit more about quarks and what happens when they get put together. So if you guys have any questions on fermions, bosons, etc., antimatter, and so on, just please ask away. Harhi matters. Yes, it's the Diddy girl from the really old 1980 anime. So true. But yeah, so let me know if you guys have any questions thus far. If not, I will start on the last part of the presentation. So the last part of our presentation is going to be about this other particle guy called lambda particle, lambda baryon. I kind of might be using those interchangeably because we first need to talk about what is a baryon. So let's try to talk about that. So I bring up our little particle model once again. And now we're going to be focusing on, so we talked a little bit about our leptons and about our electron and the positron, and now we're going to be talking a little bit more about quarks. So quarks stick together via the strong nuclear force. Yes, quarks matter. So true. And what mediates this strong nuclear force that makes these quarks stick together? And that is our guy called the gluon, which has a really good name, gluon, because it glues our quarks together and doesn't let them go. So you don't ever find quarks in just by themselves. You only ever find them glued together by the gluon. So the way that the gluon mediates the strong nuclear force, we can think about it analogous to the way we think of the photon mediating electromagnetism, just to get an idea of how this all sort of works. But now let's talk about how you can put these quarks together, what you can do with them, and so on. So when you put two or more quarks together, you get something called a hadron. We already said that word before when we talked about the Large Hadron Collider. So hadrons include two groups, the mesons and the baryons. So let's talk a little bit about those two groups. Very, very quirky. So all these hadron guys are made out of quarks. And we put them together in baryons or in mesons. So just going over this part, mesons are a group of two quarks together. And examples of that include pions and kaons. And yes, that sounds like kaon, like the anime K-On! So I just thought I would mention it. But yeah, so there's a group of particles called kaons. But we're mainly you react in the chat. But yeah, so kaon makes a surprise appearance in the Harhi stream. But yeah, so our baryons, where we're gonna have our lambda baryon, which is our interest for this, is when you put, instead of just putting two of these guys together, you actually put three of them together. And in our baryons, we actually have two particles that are very known to us and that we have talked a little bit more about, which are the proton and the neutron. So both the proton and the neutron are baryons composed of up and down quarks. And then when you put more of these charm and strange and anti-charm and so on, then is when you get some weird stuff happening. But when you only have ups and downs, you have protons and neutrons. Yes. And the quarks remain together into baryons and mesons by the strong nuclear force mediated by the gluon. And our lambda particle that we're going to be discussing from the opening is, in fact, a baryon, and it looks something like this. So we have our up, our down, and then we have another suspect. We have the strange quark. So one of the little strange guys that is a little bit higher in energy and is not as known to us, I guess, that we don't see in everyday life. But yeah, so this is our lambda baryon, has an up, a down, and a strange quark glued together by the strong nuclear force mediated by the gluon. Just repeating it so you guys get all the questions right in the quiz, obviously. Anyway, so how did they discover this lambda baryon guy? So once again, we have a cloud chamber experiment, this time from 1947, so a little bit later. I again linked the original article that showed the evidence for the existence of a new unstable elementary particles. I don't know why it said particles, but maybe it's my typo, but I don't think so. I think I copied it. Oh, of new. I thought I said of a new. I am stupid. I can't read. Anyway, so this article talks, Nature article talks about the discovery of this guy called the lambda baryon. And the way the lambda baryon decays, the neutral case of the lambda baryon, it decays into a proton and a pion. And you, in fact, see these two traces right here. There's a bunch of other particles in the back and so on. But by the way the magnetic field for this cloud chamber is directed and the conditions that are applied, they, in fact, saw that these two particles could only be explained by their mass and so on, and how fast they were going. It could only be explained that it was this guy called the lambda baryon. But however, the lambda baryon itself is in fact a neutral particle, so you wouldn't see it directly in this chamber, because this is you only ever see this through the ionization of your cool super super saturated alcohol vapor. But yeah, so you wouldn't see the lambda baryon itself, but you do see the trace product. Are they called pions since they're related to the constant pi, or is it just a naming convention? They're called pions because they use the letter pi to represent them. But to my knowledge, I don't know if the name that they chose had anything to do with it, but mathematically, I don't really think so. But yeah, they're just called pions because they use a pi symbol to represent them. But yeah, so main thing here is you can look at particles and find particles through their decay products, but sometimes not through the particle itself, because it's sometimes a very unstable particle that doesn't last long enough to be detected by itself, or in fact because the particle itself is neutral and you can't really see it in, for example, such a scheme where you have detection through ionization, which is often the case. These streams go so well with a cold beer, very relaxing. Boruto reference? I don't know. I didn't watch Boruto, so sorry. But yeah, so this is basically our last particle that we are looking at today. So now just a little bit of an overview of this detection through reaction products. That's very kind of sus. We can talk a little bit more about this in depth if you guys are interested. But basically, this is actually the way that most new particles are discovered. And this is done through analyzing decay or reaction signals in colliders. So by looking at what these particles turn into, you can kind of reconstruct what the properties of this particle had to have been for it to cause these reaction products. And the larger the the larger the collider you get, the higher energies you can accelerate your particles to. And that also means creating more particles because you have this mass energy equivalence. And for creating certain particles, you have this threshold energy that you need to reach to produce these reaction products. And this brings me to this last just showing. This is currently the largest running collider to date, which you can find at CERN. And it's called the LHC. We mentioned it briefly, the Large Hadron Collider, where they mainly work with colliding protons with protons in this large accelerator ring. And there's a few different experiments that all work on detecting a bunch of these other particles. So that's kind of a little overview. That brings me into the giveaway part. So we definitely will do the quiz very soon, but feel free to ask any questions first. And just before I answer anything, so feel free to ask while I just say this. This is a cool place where cool, strange things happen. So I think Haruhi would be interested. Note, but I was just a little bit more about these particle discoveries and other experiments that happen. So let me know if you guys are interested in that, because we could relate a lot of this to what's it called? To the second Haruhi opening mainly. I don't think my mic should be muted. I think it should hopefully be working. I had that issue at the beginning though. But yeah. So, any questions? I think there were a couple of questions previously. Some talk about beer. I'm sorry, I don't drink any beer, so I don't know. Are there any specific materials Our goal was reached. Thanks for following Downy Dolphin. But yeah, are there any specific materials obtain this particle? So more than obtain them through separating something, you're basically shooting really high energy protons. Sometimes it could be to a some sort of object, like for example, sometimes they will use lead and they will shoot really high energy protons into lead and see basically what comes out of there. But most of the time you're colliding protons with protons themselves. So you have two beams of protons that are going I hope that's very illustrative. Okay, people are talking about drinking Japanese beer. I think we're getting a little bit too drunk in here. But anyway, so depending on their energy, they create different particles. It, in fact, partially depends on the energy, but it also depends on statistics, chance, possibilities of what you could get, and just conditions such as acceleration and so on. Well, where do these protons come from? Yes, that's actually a really good question. And so CERN is a large place. So I don't think this is the best picture, but somewhere inside of this big ring, you have a smaller ring, which, you actually have two smaller rings. So it starts off with a linear accelerator that accelerates protons initially to a certain velocity, and then sends it into one circular collider, which then sends them to a second larger circular collider, which then sends them into this even larger LHC collider. And the protons from this linear collider initially come, I believe, mainly from some ion reactions where they get the protons and so on. We could talk a little bit about the physics of that. I personally don't know the specifics right away, but this is a large process, and this is in fact why America in particular failed in building their collider system, because they went into the desert and they said, we're going to build a giant collider here, and they didn't have some sort of already existing infrastructure to build a collider. And when you don't have anything, it is very difficult to achieve these really high energies. You cannot just go from 0 to 100. It usually starts with having a smaller system of colliders that then builds up into this larger system. So CERN was not built in one day. They, it was a long process of building step by step until they found stuff. They would go larger, found stuff, they would go larger, and then eventually culminating into building the LHC. Let's see. Okay, let's see. Let's look at the questions. DVC edits. I don't watch Dragon Ball. So I hope I explained a little bit about where the protons come from, but it's a complicated process. I love physics tattooed on my face. I don't want any tattoos, sorry. But yeah. So this is it from the presentation part. And let me know if there are any questions. But meanwhile, I will pull up the quiz part of things. So yeah, there's a quiz. So thanks for following Mroki. There's a quiz to win this beautiful CERN lanyard. Okay, I gotta hope you guys can see it. So thanks for following Twisty. I'm sorry, Twistive. Thanks to anyone that followed today. But anyway, so I have this cool CERN lanyard that I'll be giving away to the person that wins this quiz. So yeah, so get your phones ready, actually. Get your phones ready, because it's gonna be a quiz on Kahoot. Okay, so yes. Okay, I think you guys should be able to see it. So I'm just gonna, I don't want music. But anyway, so log into kahoot.it, or if you have the Kahoot app or something, and you can use this pin to join chat. Goodbye. Yeah, if you fail, you have to rewatch the video on demand, of course. But yeah, lock in. I don't think the questions are really hard. I personally think probably most of you guys will get them right. But yeah, if you are right and also fast, then you may be able to win this really cool lanyard. Yeah, so we have 6 people at the moment, so let me know if you guys are still joining, and then I'll wait a second. Okay, we have 7 people joining. Pretty cool. Okay, we're at 6 people, but yeah, let me know if you guys are still joining, and then I'll wait a little minute or so for you guys. Okay. I'm just here for the physics and beer. I'll drink to that. Okay. So, if we're good, then I think we can get started. So, let's get started. So, our first question is the first question, there is no wrong answer, but it was, what is your favorite topic today? Did you like discussing positronium? Did you like talking about the lambda baryon the most? Energy, mass, equivalence principle, or the wave equation? So you can vote which one is your favorite. So yeah, there is no wrong answer. Okay, so a little bit split. We had a little bit of everything. I think that's cool. Our next, okay, so it still gave you points because of how quick you answered, but hopefully it won't skew the results too much. But yeah, let's move on to the next question, which is, how much is the relativistic mass difference when you charge an electric SUV battery? I think I am kind of on the way of the question, so I will just move my screen. But yeah, how much is the relativistic mass difference when you charge an electric SUV battery? I think maybe you should be able to see it a bit better. Nope. Okay, let's do it like this so you guys can actually read the whole question. Next time I will actually fix it. But yeah, so 3 people got it right, and that should be a few micrograms. So yeah, an electric SUV battery only changes a few micrograms when you charge it. So we have Tsumi leading the charts right now, so good job. Frolic was the only one that liked the wave equation. I think you're the math guy, right? So I guess that makes a lot of sense. Let's see. So you can directly detect neutral particles in a cloud chamber. Is this true or is it a false statement? Can you directly detect neutral particles in a cloud chamber? So lock in your answers. True. No, you cannot directly detect them. Maybe this was a tricky one because of the language. You can only detect their reaction products, but you cannot directly detect them because cloud chambers work through ionization, and you cannot ionize with a neutral particle. So let me know if that was unclear, but it was kind of a tricky one because I used the word directly. Yeah, Tsumi's still going at it. Crazy. So next question, what particle mediates the strong nuclear force? Is it the Higgs boson, the photon, the gluon, or is it the electron? So lock in your answers. Which particle mediates the strong nuclear force that, maybe as a reminder, glues the quarks together? So let's see. And yes, the gluon, correct. So only a couple wrong answers, so it's okay. Let me know if anything was unclear, but yeah, our gluon mediates the strong nuclear force and glues quarks together. So Tsumi's still going at it on a four question streak. So good job, Tsumi. Let's see. What is the most common product for electron-positron annihilation? So what do we get out when we have an electron annihilate with a positron? Do we get 3 photons, the Higgs boson, positronium, or do we get only 2 photons? So lock in your answers. What do we get when we get electron, positron annihilation? Correct. We get 2 photons. Positronium, we don't get it through annihilation, but it's simply a bound state between the electron and the positron. So this is simply a temporary state where they are basically what you call like metastable, like stable for only a little short period of time. But yeah, when they annihilate, you get 2 photons out of it. So good job, Sumi. Still going at it. And yeah, next question. Light always travels at the speed of light. Is this correct? So yes. Or is it incorrect? So no. Does it depend on the medium that my light is going through? Or does it depend on the wavelength of my light? So look in your guesses. What does this depend on, if it even depends on anything at all? And yeah, correct. There were 2 correct answers, in fact, and that is that it either depends on the medium or the wavelength, or both really at the same time, because light propagates differently through different media, and in fact, the frequency of light also matters as to how it propagates through this media. And light always travels at the speed of light only in a vacuum, but whenever we get into traveling through a medium, then it does not really propagate at the speed of light, but it propagates at a fraction of the speed of light. So speed of light is basically the maximum that it can really reach, and this is only when it's traveling in vacuum. No, it's okay. No one is stupid. A lot of these were kind of tricky, I will admit. A lot of these were a little bit tricky questions just to check for understanding and to check that the wording is a little bit tricky. I will admit. But yeah, let's look at the next question. Okay, Sumi's still going at it. Good job. Darren says, second right answer. Let's go. Let's see. So this one is a funny question. Which is not a type of quark in the standard model? So which of these did we not mention at all because it doesn't exist? Is it the top quark? Is it the strange quark? Is it the hex quark? Or is it the charm quark? So, correct, everyone. Okay, the top quark. No, the top quark is real. The hex quark is not real. And I actually just asked ChatGPT to give me a list of fake quarks, and I just chose the one I thought was funniest. ChatGPT gave me some pretty funny answers, I will say. But yeah, so this was a fake quark that was made up by ChatGPT. Let's see. So, Tsumi, someone is catching up. Is Mrauki? And we have plan with the highest answer streak of 5. Wow, let's go. It's kind of getting closer. It's getting a little tighter. Let's see. We have a few questions left. So the energy of a photon is continuous. Is this correct? Is the energy of photons continuous? Let's see what people think. Okay, maybe I worded this wrong, or I worded this in a way that can be taken wrong. But okay, I was really tricky with this, I will say. The electromagnetic spectrum is continuous, but the energy a photon can carry is quantized. It is not continuous. And this is particularly what we discussed when we discussed quantum mechanics. So photons only deposit quanta of energies. So not a continuous flow of energy, but quantized depositions of energy. So maybe I was a little bit mean with the wording and putting a picture of the electromagnetic spectrum. So I am sorry if this was really misleading, but I was kind of getting at the fact that photons deposit energy in a quantized matter and not in a continuous matter. So let me know if that was unclear. I'm sorry if I confused you. Let me know if that was unclear. So I am sorry only one person got that one right. I'm sorry. Okay, so Rauki has 6 correct answers. Perfectly fair and balanced. Yes, I was a little bit tricky with that one. I am so sorry. But yeah, let's move on to question 9. Which of these particles was first discovered at the LHC? I think I only just briefly mentioned this, but I did show how 2 of these particles were discovered. But yeah, okay, the Higgs boson. So yeah, 3 people got it right. So no, the lambda baryon was discovered in a cloud chamber experiment, not at CERN. Not at the LHC. The LHC was built sometime in the 2000s, I think. Late 90s, 2000s. And positrons, no one voted for that one, okay. Photons, no, photons are, photons are light. We knew about those before the LHC. Luckily. But yeah, the Higgs boson was first discovered at the LHC. And I am so sorry if these are so tricky, and I was a little bit mean because I thought I was making it simple, but then I was like, I need to be a little bit tricky with the questions. I am sorry. No lanyard for me, just gotta go to Switzerland myself. No, Frolic, I'm so sorry. In a fetal position right now, I'm so sorry. We still have a couple questions left, so don't lose hope. We have Miyauki, who right now is on the lead, but we have a couple guys that are not so far behind, so let's see if this makes or breaks it. So which of these particles is made out of quarks? Is it electrons? Is it lambda baryons? Is it protons? Or is it gluons? So which of these particles is made out of quarks? I just added our standard model. Maybe it's a little bit helpful. So yeah, which of these particles is made out of quarks? It could be protons, and it is also lambda baryons. So yeah, both of these are a type of protons, and it cannot be the electron, and it can also not be the gluon, because the electron as well as the gluon are elementary particles, meaning that they're not made out of anything else. So if they are in this list, they are elementary and they are not made out of anything else. However, lambda baryons are baryons, which are made out of 3 quarks, and similarly, protons are also baryons and also made out of 3 quarks. Can we include differential and integral calculus? I'm trying to make the quiz a little bit more inclusive. So we have Mrauki still leading with an answer streak of 8. Good job. I should have been paying closer attention to the stream instead of playing Crusader Kings. Very true. You can watch the video on demand as punishment. Okay, and this is our last question that is not with all right answer, which is, which of these is an elementary particle? Is the proton an elementary particle? Is it the electron, positronium, or the neutron? So again, elementary particle is a particle that is not made out of any other particle. It's just a particle that cannot be split into tinier particles, basically. So which of these was in this elementary particle model? And yes, the majority of people got it correct. It's the electron. The proton is a baryon, meaning that it's made out of several quarks. Positronium is a bound state between an electron and a positron, meaning that there are 2 particles involved in there. And no one voted for the neutron, which also it's another type of baryon made out of 3 quarks. So Mrauki, good job. 9 correct answers in a row. Very impressive. So our last question is not a right or wrong question, but I wanted to see some opinions. So our last question is, if Haruhi were an elementary particle, which particle would Haruhi be? Would Haruhi be a strange quark? Would she be a Higgs boson? Would she be a charm quark? Or would she be an electron? And I hope I see yes. Okay. Strange quark definitely won. And that would have also been my answer. But yeah, I just wanted to give kind of a subjective question with no right or wrong answers. So good job, Mrauki. Send me a message either on Twitter or just here so that I can ship you your CERN lanyard. So congratulations, Mrauki. Just send me a message so I know who you are, and I will ship it as soon as possible. And also, good job, Sumi, and good job, Plan, for getting also a lot of points. Also, a really good job. So, yeah. So good job, everyone. I hope it was not too mean. We have a little bit of a summary. So I will say maybe I went a little bit too hard in there. Maybe I went a little bit too hard in there. But yeah, shouldn't have dropped physics for graphic design. I kind of wanted to study graphic design when I was like 12, 13, and I ended up studying physics, so I kind of took the other route. So yeah, Mrauki, just message me and I will get your lanyard shipped as soon as possible. Going to Switzerland tomorrow, yes. Should have included differentials, but that's just me. True, I should have included just for frolic next time. I really should have included the question, what type of differential equation is the wave equation? that would have been a good question, honestly. I didn't think about that one. I should have included that one just for frolic, because he's the differential calculus guy, I guess. So let me know if you guys like this format with the little questions. I don't really have a lot more certain lanyards to give away, but I could do like a little giveaway once in a while. But yeah, let me know if you guys have any questions as to what we discussed today, just out of curiosity, what the heck are these particles? I thought first time I heard about all these particle stuff, I was like, what the frick is all of this? But I hope I gave you guys a more or less comprehensive overview. And yeah, if you guys are confused by anything, please just ask. If you guys were confused by any of the questions, I feel like the one that brought most people to confusion was the one about the photon energy. So maybe I was a little bit unclear with the language there, but what I meant is how do photons carry energy? And it is from what we saw last week, if you guys didn't, or 2 weeks ago, it's in a quantized way. So please ask away. I still have a little bit of time to answer some questions, or just, it doesn't have to be just physics, could be like whatever. But yes. Let's see. Yes, it wouldn't have been fun if the questions were too easy. And also, at the same time, I will admit, I'm not saying this as a dig or anything. I feel like I just have a little bit of a skewed view of all of these subjects. So it is good to be in tune a little bit more with just general, what generally people like. And obviously it's really difficult to just absorb all of this information in an hour and a half. So I yes, yeah, sorry. I expected the quiz to be easier, so I am so sorry about that. Rauki, my DMs are locked, or blocked. On Twitter, maybe if it's on Twitter, just tweet at me and I will follow you, so you can also DM me. If it's not on Twitter, maybe I also have my Instagram linked. I think that one should not have DMs blocked. But yeah, I hope we can figure this out in the next. If not, I will just DM you after the stream over here. Worst case scenario. Okay, let's see. I have a difficulty picturing the equation of particles. Yeah, so I mean, I feel like the wave equation is a little bit of a difficult one to picture if we're not looking at the solutions of the wave equation. That's why I didn't really want to focus too much in there. However, it's on the opening, so I wanted to at least mention it and kind of just tie it to photons and how we describe those as okay, add Maki on Twitter. Okay, I will DM you after this stream then. So congrats for winning. So plan from space, you have to go now, so bye. Thanks for watching. Frolic has class again. Frolic, go to class. Stop forgetting. Go to class. My favorite color is blue, I would say, kind of like turquoisey blue, like a Miku greenish blue. So Zoaos is leaving, so bye Zo, or Z10os. Okay, I don't know, but bye. Oh whoa, Axis asks, he's curious to know, or she is curious to know, how I studied all that. So I got interested in physics primarily when I was a kid, I guess, a bit, but I mainly got a bit more in depth into physics when I was 16 or 17, like starting to figure out what to do with my life after college. Initially at 14, I was really interested in astronomy, but I quickly lost that interest as time went on. And yeah, when I was finishing high school, I started listening primarily to a lot of podcasts on the topic of primarily particle physics, actually, and that really got me interested in all this particle stuff. There was something, we can get into the history of it, but it's really interesting. There was a period of time that people called the particle zoo, because there were so many particles that they started discovering that it was like, oh, new particle every week, like it's like a zoo, like you just have all of these animals, like all of these particles that you're just discovering here and there. And that was like really crazy time in physics, and just hearing about this sort of physics renaissance or particle physics renaissance really personally really interested me. But yeah, so I initially started studying that, I guess, more so as a hobby, sort of just for my interest, but I didn't really get to look at all the theory and so on behind it until I started college, and I had this like particle physics lecture, I think on my second year of college or something like that. So yeah, but I think there's also a lot to learn through podcasts, movies, even YouTube now. There's a lot of really good physics YouTubers, and obviously through streams as well. But yeah, so I hope if you guys are interested and you can find the resources, even ask me, even just ask me like, sorry, even just ask me, what's a good book that you would recommend, and we can discuss like what your math level is at, how much you're interested in learning, and so on, and I can definitely help recommend something to you. Okay, I ramble so much. Riyadh asks, favorite street food. I actually don't eat a lot of street food, but maybe hot dogs. I like hot dogs. I I think hot dogs, I guess. Listening to the stream while I studied linear algebra. Yeah, linear algebra is rough. I will be honest. Like, if you say linear algebra, it's like, okay, diagonalize matrices, get eigenvalues, get eigenvectors, and that's kind of where my knowledge tapers off. Basically, only the stuff that I needed for quantum mechanics and so on. Linear algebra is easy if you are talking about linear, like if you're talking about regular linear algebra, but whenever you start discussing, like different bases and so on, it gets pretty quirky. At least to me, I always find that really hard to imagine, honestly. And that you kind of need a lot of if you are doing any sort of, especially general relativity. And I just could never get into that. That's just too crazy for me. At least I still have yet to receive any formal education on general relativity. That stuff is pretty crazy. Anyway, linear algebra is directly tied to computer science. But I think you're probably referring more to all this, matrices, diagonalizing matrices, extracting eigenvalues and so on. Like, I think that part is fine. But the other stuff, I don't know. When you start talking about tensors and stuff, I don't know. I don't know. I had like a whole lecture on tensors and like covariant, and don't get me started on that stuff. Random song fact: CCOF is doing numbers in Russia and Ukraine. What a funky combination. That is funny. That is funny to know. I'm glad we're uniting. We're uniting it during the war. Let's see. Well, sorry. I prefer to ignore everything I don't need and pretend I'm smart. True. That's what I'm saying. Like, when you say linear algebra, I think like, okay, I got this far. This is as far as I need to go for my own personal purposes. Despite saying Steins Gate is mid, I think you would probably look very good in a Curse of cosplay. I actually do like her, I will say. Okay, I will, controversial subject. Yesterday I said I don't like Steins Gate that much. I personally found the plot itself a little bit cringy because I already knew about this whole like John Teeter like internet hoax about this like blog where some guy used to post about like time traveling and stuff like that, his predictions, and that also I guess it just made me cringe a little bit because I knew about that before. And then also on top of that, I just found the general like time travel plot to be, for my own personal taste, a little bit lackluster. But I do like the characters. I think the girls in the show are pretty cute. And I don't hate the show. But I always just found it, and the word that I use is I find it really overrated. Because I guess from so many people recommending it to me, I actually did. So just clarifying my views on that. Okay, let's see. Some more questions. Or just comments. In English, it's called diagonalizing, but there's a totally different name in Portuguese. In Portuguese, it's called taking the determinant. So taking the determinant is not the same as diagonalizing, right? So taking the determinant is like, there's different ways of doing it, but like, for example, when you have a 2x2 matrix, you just go this guy multiplied by this guy plus this other guy multiplied by this other guy, and then I think a minus sign, something like that. I haven't used linear algebra in a while, but yeah, minus sign because you're going the other direction. When it's 3x3, it gets more complicated, blah 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 blah. But yeah, that determinant is not the same as diagonalizing. Diagonalizing is when you have a matrix and you want to reshape it so you only have entries in the diagonal entries where basically like 1 1 2 2 3 3 and so on. So those are slightly different just different things that you need to do. I was not expecting talking about linear algebra, like discussing linear algebra in the stream. I need to brush up on linear algebra. I always whenever I have to do something, I'm always like, oh crap, I have to remind myself what the frick is going on in linear algebra. In Portuguese, transposta. Transposed? Was that not something else? I forgot linear algebra terminology. Transposed, is that not like the -1 notation? What was transposed matrix? Yeah, it's when you take it and you basically like sort of flip it, right? It's a little bit also slightly different than diagonalizing it. Just the notation is, let's see, diagonalizing a matrix. Let's see, I just looked up diagonalizable matrix. Let's see what it's called in Portuguese. Thank you so much, Dahlia. Thank you so much for the gift. Thank you so much for gifting the sub. Let's see. Portuguese. Matrix diagonalizável. I probably just insulted all the Portuguese people in the chat. Diagonalizar with like an apostrophe. Sável. I don't speak Portuguese. I am so sorry. But yeah. Portuguese, yes. Spanish stream 1. I don't know if I've ever planned to do a stream in Spanish. I feel like I just sound less, especially when we're talking about physics. I could never talk physics in any language other than English. Maybe a little bit German, but just English is better. I feel so much more comfortable talking about physics in English. That's the way we speak. Yeah. Okay. Diagonalizável. I don't know. Something along those lines. But yeah, so that is when you have just entries along, your 1 1 blah blah blah, and then all around that you have 0 0. So a little bit different than transposed, a little bit different than determinant. All of this just like reminded me like I really don't remember linear algebra. But yeah. So yeah, I'm starting to zone off and ramble so much. So I'm sorry about that. But yeah, so let me know if there are any other questions in general. If not, this will also be uploaded on YouTube eventually. You can also ask some questions over on YouTube, and I will do my best to respond. You can also DM me or just add me on Twitter. It's probably the place where I respond the most. I also have my Instagram linked. But yeah, if you guys have any questions, please feel free to ask anything about what we discussed today, or just about resources, where to learn more about this, all of this stuff. Sorry. And also, if you guys are interested in maybe just a more extended chat about all these topics, because there's so much to say, and yeah, it's hard to condense it into just 2 hours. So you can definitely do like a whole review of all this stuff. Definitely. I took Friday off for the first time in forever to play Fortnite. and tune into the stream. Very good stuff. Awesome. Yeah, I need to play the new season that just came out. I haven't done that yet. Daliard says he needs some more book reference. Yeah, just DM me. I'll send you some stuff actually. For this is a funny story. I was at university yesterday. I pulled out my book and I'm looking at this book on, like, just introduction to particle physics. So I was just kind of brushing up on stuff just to not come unprepared, and someone asked me, like, what are you doing? And I'm like, okay, I guess I have to kind of explain what I'm doing. And then I feel like I just end up rambling too much, and I just ended up rambling like, oh yeah, and there's this like problem about this anime, which is like a math problem that had never been solved before this anime, and I just ended up rambling so much, and I'm like, this is why no one talks to me. What is wrong with me? So yeah, I talk too much and I ramble way too much. But anyway, I have some books, some introduction to particle physics books that I can definitely recommend. Rambling again. Is it true that thing that scientists really thought the moon was not there when we looked at it during the 20th century? So maybe I mean I don't know, honestly, personally, but I can look at some historical views on things. Like, actually wanted to kind of include this. Wait, let me look it up so I don't get it wrong. Yeah, the electron. I kind of wanted to include this just because it's a funny, like, just historical fact. The electron, when it was first discovered, they call it the corpuscle. The corpuscle. I am so glad that I don't have to say, yes, the corpuscle and the anti-corpuscle. That would have been so awful, I will say. That would have been so awful. But yeah, the corpuscle, that's just such an awful name. I say Strange Quark, Charm Quark, those are good names. Those are names that I like. The corpuscle, no, the corpuscle, not a good name. Daliard is naming his next dog Corpuscle. Please don't, Daliard. Please name him like Strange Quark. That's a good name. Oasis also on some reference. Maybe we'll try to include just some general references on the YouTube. On the YouTube video on demand. And also, like I mentioned at the start, I included the slides for the presentation, so with all the links that have a little bit of additional information and so on, and those are all included in my Ko-fi page. I also would really appreciate any donations. Shameless plug. But yeah, they can be downloaded for free, obviously. And you could also look at the video on demand for just the names as well, if you don't feel like downloading that. But yeah, I have rambled on too much. When you start talking about diagonalizing matrices, I think you went off the rails, I will say. I think that it's too much. It's too much. But yeah, I will try to include some references, or just maybe not references directly to what I talked about, but just some general books to talking about all this stuff. Yes. A paycheck for my work in the song. That's awesome. That's great to hear. That's great to hear. Awesome. Thanks, Sinister Fua. We love diagonalizing matrices here. I will say I have probably diagonalized like 3 or 4 matrices in my entire life. It's not something I think about every day. I don't know why that was the first example that came into my mind about discussing linear algebra. I don't know why. I have taken probably hundreds of determinants and extracted hundreds of eigenvalues and eigenvectors, and I have maybe diagonalized 4 matrices. But, V-Bucks is payment, obviously. I think V-Bucks is probably the best currency at the moment. Obviously. You know, with all the Miku stuff coming out, you can't have enough. You can't have enough V-Bucks. The diagonalizing tangent, no, just awful. It needs to stop. It needs to stop. Too much talk on diagonalizing matrices. I don't know why that was the first thing that came to my mind. That was an awful example. That was a really bad example. Anyway. But yeah, last chance. Ask some last questions. Ask some last questions if you're interested. Meanwhile, I will find the winner and send him or her a message on Twitter. ? Yes. So yes. Okay. Okay. But yeah, so if you guys have any last questions, please just let me know. I will try my best to answer them. All right. Okay, so I messaged the winner. And yeah, if there are any last questions, we can definitely have a quick discussion about that. If I can read the chat. Okay, Sinister Fua is leaving. Goodbye. But yeah, so things are coming slowly to an end, I think. Can we retake this test later? Of course. Of course. Yeah, I think the test should be saved, and if you're interested, I can send the questions, or else you could go through the video on demand and try to answer them, then remember what you answered first and have a better answer next time. I don't want to fail this subject. What happens if you fail? If you failed, you have to watch all the video on demands, donate $5 and then you can retake the test, and then you can move on to the next part. No, I'm kidding. I mean, yeah, I will try to do more quiz stuff in the future, because I feel like that was funny. RX7 Slayer's leaving. Bye Slayer. Yeah, so just quick recap and just what is going on next, blah blah blah. So we're close to finishing the Haruhi, the Bouken Desho first Haruhi opening series. I will do one last stream in 2 weeks, which will cover more non-physics topics, so maybe stuff that some other people are more interested in, a little bit more statistics, I guess a little bit more computer sciencey. So I know a few of you guys studied something more along those lines. Maybe you guys will find that more interesting or will do better at it. I personally have more of just a general physics background, so might be a little bit more from that perspective, but I hope we can reconvene these two perspectives into something interesting. And we're also gonna have a chemistry thing, the only chemistry thing in the whole opening. So that'll also be a subject that we will discuss. Sinister Fu is pressing the song on vinyl. That's really cool.